Another type of popular problem in physics classes are pulley problems. And again, this isn't really something you'll realistically ever have to deal with in your careers. But the important part is it's an application of using this problem-solving framework to try and solve a puzzle. And if you look at it like that, then it's actually still very useful to have this method. Okay, and to solve problems like this. So again, we'll call this mass 1. We'll call this mass 2. So we'll say that we have two masses that are connected by a rope that goes around a pulley that's free to turn. And we're going to make the pulley massless. Now, in this course, we're not actually ever going to put any mass on the pulley. If this were the engineering course, that's something we would look into. But I will, make a quick comment on, why massless. In other words, how would having a mass change the system? So let's imagine what would happen. We have two blocks. Let's even say that this is frictionless for now, so that block 1 is just going to slide with no friction. So if there's no friction here, we know it's going to move because there's nothing to hold it back. So these blocks are going to move downward. And as you can imagine, you have potential energy. When the blocks are at this height, and then as block 2 falls down a distance x, it will have a change in potential energy minus mgx, and that all goes to the kinetic energy of the system, 1/2 m1 v squared plus 1/2 m2 v squared, right? And so mgx is equal to the kinetic energy. Well, if we had a mass of the pulley, right, we've talked about rotational energy already. We know we'd have to add a term 1/2 I, the moment of inertia of the pulley, times its angular velocity squared. So you see that having a pulley there is actually going to change the dynamics of the system some. So we're not going to worry about that. We're just going to assume that our pulley's massless. So we're not going to lose any energy to that. And because of that, it means that the tension on this side of the pulley is the same in the opposite direction as the tension on the other side. And again, this is only true because we're using a massless pulley. If the pulley had mass, you'd see that this actually wouldn't be true. The tensions would be slightly different. Okay. The other thing we're going to do, we want to notice, is when we work a problem like this. Okay. So of course, here we would say that this is the y direction, and we have the x direction going to the right. So the y direction's up, the x is to the right. But notice that we can really treat this system as a one-dimensional problem where we have two masses that are connected by a rope, and we have a force in the x direction, which is the gravitational force on block 2. So these two problems are mathematically equivalent. So it's easy for us to think about now. We actually kind of rotate our axis, so this is the y direction and this is the x direction. So we look at this, we take this system that seems to be in 2 dimensions and we make it a one-dimensional problem. We did something similar with an inclined plane, although in that case we just rotated it. In this case we're just kind of rotating part of it. Okay, so now we can set up our problem. We say that the net force, so we'll look at block 1 first. So we know that we have a normal force and a gravitational force, m1g. On block 2 we have m2g and a tension, and of course block 1 had a tension as well. So now if we look at mass 1, we see that the net force is the normal force in the y direction. And let's say that there's friction now, so we'll add in friction here. So we have a frictional force in the minus x direction. So we have a tension force in the y direction. We have a gravitational force in the minus y direction. We have a tension in the x direction. And we have a frictional force in the minus y direction. And that's going to equal the x acceleration and 0 in the y direction because this block isn't moving up or down. Okay? And so then when we do that, well, we say that if we look at the y components now, this means the normal force is just m1g. It means that the frictional force is mu m1g. And so now we can solve for the acceleration. Oops, I keep doing this in these videos. I'm not sure why. Okay, so mass times acceleration is equal to the tension minus the frictional force, which is the tension minus mu m1g. Of course, this should be a 1. And so this tells us that the tension is m1 times a plus mu g. Now if I look at mass 2, again, I haven't really solved the problem to find what the tension in the rope is because I still don't know what A is. So now I look at mass 2, and I say now the net force, F net, is equal to, so now I've defined this as my x direction, right? So this is mg in the x direction, 0 in the y direction, plus the tension, which is minus f of t in the x direction, 0 in the y direction, and this is equal to m2 a in the x direction and 0 in the y direction. So now I see that I get another equation for tension, which says the tension is m2 g minus a. And so once I have this, then I can say, okay, well, I know that this is, I can go back and pull, sorry, not there, right here, I have my formula for tension from the first equation. I'll set them equal to each other, so this is equal to m1 a plus mu g. So now I've gotten rid of the tension, and I have an equation with only one unknown, the acceleration. So now I can find the acceleration of the system. So I'll pull this a over to this side, I'll pull the mu g over to this side. So I see that m1 plus m2 times a is going to be equal to g m2 minus mu m1, which means the acceleration is g m2 minus mu m1 all over m1 plus m2. So if I look at this, I see that my units match. I have acceleration on this side, and then that's multiplied by a mass term, but the mass terms cancel on the bottom. So my units check. And now let's see if it makes sense. So now we're saying that if mass 2 is greater than the coefficient of friction times mass 1, that we're going to have a downward acceleration. And that's what we would expect. We have a net force to the right, basically, like our net force to the right is just going to be the gravitational force, because if we look at the one-dimensional problem, we see that tensions cancel themselves out. So the only force really working against us is the force of friction. So if this force is bigger than the force of friction, then we'll have motion, we'll have an acceleration. Of course, if the term on the right is bigger, it doesn't mean we'll have a negative acceleration, right? It's not going to go back up. It just means that the acceleration is 0, and so that would give us a way to solve for the coefficient of friction, for example. And so that's really all there is to solving a pulley problem. Now you can get more complicated problems. Again, we're not really going to do any of these in this section because it's a bit more work. But for example, I've seen, problems before where you have something like this, and so you can have, you can have a mass here, and there's a pulley that connects it, and it comes down here, and you have a mass 2 here, and then this can come back up to this pulley, and this comes back up to a mass 3 here, and then you have to find out, what direction the motion is going to be. And so this can be a much more difficult problem, and this is a problem that I've seen before in the engineering section of this class, but it's really no different than the way that you would solve the problem that we just had. You would go back to summing the forces and setting up your equations, your net force equations, solving for the accelerations or the tensions, and in the end you would get an answer just in the same exact way.